Welcome to section 3, training a supervised learning model. This is lecture 11, training an XGBoost model. So this section is an attempt to build upon the initial work we did with the logistic regression, where in a supervised learning context, a logistic regression model acts as a very good baseline, effectively. But often once we've built a baseline, what we'd like to do is to iteratively build more complex models up until a point that we can prove that the additional complexity does provide better performance from a classification perspective. If not, then by all means, default to your logistic regression model, because if it's simple to implement and it gives you good enough performance and it runs pretty fast, you can interpret it quite easily, then it makes sense to stick with that. Simpler is better. But if it's a high stakes game and it's worth the additional complexity because you get those additional performance gains from a classification perspective or whatever else, then obviously if you can equate it to a monetary value or something like that, then potentially it makes sense to look at more complex approaches. And one of those that does work very well on tabular data is XGBoost, which is a popular and efficient open source implementation of the gradient boosted trees algorithm. And gradient boosting is essentially a supervised learning algorithm, and it attempts to accurately predict a target variable, like we've been doing with logistic regression, by combining the estimates of a set of simpler, weaker models. That aggregates in an ensemble way a bunch of simple, weaker models to make an overall meta decision, right? So I've pip installed XGBoost onto my machine. I'm importing it as XGBoost, and it has the same API interface as what we're used to seeing within scikit-learn. So it works on the same premise as, once you've initialized a model class, you can then train the model by using .fit, specifying our training features as well as our training target variable. We train the model, and then we can say model.predict on the unseen test data to make the classifications. We can make use of the confusion matrix like we did for the logistic regression. And I've applied the same confusion matrix to print out the overall results. If I make this a little bit smaller, we can see the full picture here. So if we recall, we still had quite a few false positives with the improved logistic regression model. We were able to detect 44 fraudulent cases. In here we've got slightly less, so we've got 40, but we've got very few false positives, only 2 of them. So that might be a very good trade-off. The model's very accurate from that perspective, but maybe we're not satisfied with these 9 cases that we weren't able to detect. So there's obviously room for us to improve this potentially. Recall that this is just a baseline XGBoost classifier that we're implementing. We haven't done any hyperparameter optimization. And as you can see with this model object, there are quite a few hyperparameters that are at our disposal that we are able to optimize. That's another whole art and science on its own, hyperparameter optimization. There are open source tools that allow you to iteratively find the best combination of different hyperparameters to give you your optimal model. We won't be exploring that here, but what we will be doing is just focusing on the hyperparameters that make sense from a class imbalance perspective.